this class we see about unitary transforms and some of its properties. Here I have used a series representation of un, that is a one-dimensional sequence un, which is having a length n, that is n varies from 0 to n minus 1. Then I can represent the unitary transform, the transform coefficient b, as b equal to a into u. So u is your original input sequence. So a represents the basis. So a, that is a basis, multiplied by u, you will get the transformed coefficient v. So I can write down the transform coefficients vk. So the kth value of the coefficient will be un is your input sequence, multiplied by the kth coefficient, that is a multiplied by the kth basis function ak of n, where n varies from 0 to n minus 1. So a is a basis function, and here in the case of unitary transform, this a will be an unitary matrix. That is, a unitary matrix means a inverse of an unitary matrix will be same as its conjugate transpose. So here a inverse will be same as a conjugate transpose. So this is v, that is a transform coefficients v. Similarly, I can write down the inverse, that is u equal to u, as we say, if I have v equal to a into u, u will be equal to a inverse into v. So I have u equal to a inverse into v, where here a inverse equal to a conjugate transpose. So I can rewrite the expression u equal to a conjugate transpose into v. So I can write as a expression as u of n, that is the nth term, will be sigma k equal to 0 to n minus 1 bk, that is a transform coefficients, into ak star kn, okay, where a represents our basis. So we have the expression b equal to a into u, that is a unitary transformation for a sequence or a one-dimensional case, and u equal to a conjugate transpose into v. The same thing we can apply, we can just increase one dimension and apply in the case of a two-dimensional case. So in the case of a two-dimensional case, instead of bk, I add one more dimension. So I have bkl. I have two summation. I just increase the dimensionality. So I have sigma m equal to 0 to n minus 1, and similarly I have n equal to 0 to n minus 1. So instead of un, instead of the sequence un, I have a two-dimensional image, that is umn. Then instead of akm, I have ak, that is for the kth coefficient I have akm, for the kth coefficient I have akn. So here I have klth coefficient, so I will be having akl of mn, where again the value of k and n varies from 0 to n minus 1. Similarly, I can write down the inverse equation umn will be, I have bkl akl star of mn. That is, I just add one more dimension to get the two-dimensional equations. So here a, k, l, mn, it is actually the basis function. So if the basis function should satisfy some properties, so here should be complete and orthonormal. So completeness means when I take kl, mn, and when I take kl at different point m dash, n dash, when I take the correlation, I will get delta of m minus m dash, n minus n dash. That is an impulse function, and which is having the value 1 at m minus m dash and n minus n dash. Similarly, it should satisfy the orthonormality. That is, I take the point at two different points, akl mn and ak dash l dash mn. So again, it should give an impulse function which is centered at k minus k dash l minus l dash. That means its impulse function is having the value 1 at k equal to k dash and at l equal to l dash. So this basis function should be complete as well as orthonormal. Then this v actually represents the transformed coefficients, or we can represent the set v, that is the set v as the transformed image. Okay, the original image is transformed into v by multiplying it with some orthonormal, complete orthonormal basis function a. Okay, so here again the equations are the same. V equal to A into U and U equal to A conjugate transpose V. Equations are the same. Now, this transformed image should satisfy one condition, that is, if I take the inverse expression, that is inverse expression, I have VKL, AKL, Mn. So, AKL, Mn star. So, if I take the inverse expression and I truncate the sequence, that is K actually varies from 0 to N minus 1. Instead, I truncate it up to P, where P is less than or equal to N. Similarly, L varies from 0 to N minus 1 and truncate it up to Q, that is L equal to 0 to Q minus 1. So if I truncate the sequence like this, the value I obtained for UMN, that is by truncating to P and Q, will be having minimum error. That is, when I take the mean square error between the original value of UMN and the truncated value, the error will be minimum. That is a condition for orthonormality. That means from that, if I know the transformed coefficients, from a fewer number of coefficients, I can recover the original image. That is the advantages of using this transform. Then, one common and main property of this unitary transform is a separable property. That is, if I have AKLMN, we know AKLMN is a basis function, and this I can split as AKM into BLN. That is, it can be separated into AKM into BLN. That means if I have a two-dimensional matrix, then I can represent it as a product of two one-dimensional sequences. Similarly, here you can say this AKM and BLN have the one-dimensional complete orthonormal basis. That is, this two-dimensional basis function I can represent it as a product of two one-dimensional complete orthonormal basis function. Okay, so AKLMN I can write it as AK into BN. So usually we will choose this B and A as the same value. Okay, we choose A and B as the same value. Here I use capital A and capital B. That is, capital A denote all the set of A. Capital B denote all the set of B. So usually we choose this as the same value A, such that we can rewrite the expression for VKL as, that is, I actually have in my expression AKLMN. Here I split that into 2. I separate it into 2. That is, I write it as AKM into UMN ALN. That is, AKLMN, I split that into 2. AKM into ALN. You can just give AKLMN, I can write it as AKM. AKM into BLN. Okay. Here I use A and B as the same. So AKM into ALN. So I can rewrite the expression for VKL as AKM into ALN. Okay. Or you can write in the matrix form B equal to A into U into, this ALN is A transpose. A U into A transpose. Similarly, you can write down the expression for the inverse, that is UMN. Here also your expression was A conjugate KL of Mn. So I just split that into 2. So I have A conjugate Km and A conjugate Ln. So your expression, actual expression was U equal to A conjugate transpose V. Here I split that into 2. So I have the new expression U equal to A conjugate transpose V into A conjugate. Okay. So B was A into U. By separable property, I split that A as A into U into A transpose. So I can write it as A U into A transpose. Similarly, U equal to A conjugate transpose into B. By applying the separable property, I can rewrite U as A conjugate transpose B into A conjugate. Okay, so main advantage of applying this separable property is the computational complexity will be reduced here. That is, instead of multiplying A into U, if I use A U into A transpose, the computational complexity here will be reduced as compared to the previous case. That is the main advantages. So we know in order to compute VKL, I have to take AKLMN, that I split it as AKM into ALN. Okay. In order to compute VKL, I have to take the kth coefficients. Here, kth coefficient, I just represent it as AKL conjugate. So AKL conjugate is actually obtained by taking the kth value, that is AK star, that is the kth column, multiplied by the Lth column transpose, that is AL star transpose, that is VKL. In order to compute VKL, I have KKL of Mn, which I write it as AKM into ALN. Okay, so I have AKL star, I have the kth basis image, I can write it as kth column AK star into Lth column AL star transpose. So here given one example. By doing this example, you will be more clear. I have given an image U. U is my image, and given the matrix A. A is given. That is a unitary matrix. A is given, and U is my image, and A is a unitary matrix. We have to find out the transformed image. We have to find out the basis image, and also verify the inverse transform. So as we know, transpose image V is given by A U. A transpose will be a transpose image. So A is here. U is here. I have to find out A transpose. When I take the transpose, 1 by root 2 is common. 1 will become the column and 1 minus 1 will become the row. That is, you will be having A transpose will be same as A. So multiplying A into U, then the resultant multiplied with the A transpose, you will be getting the transpose images y minus 1 minus 2 0. And next is to find out the basis image. So in order to find out the basis image, I have A star, A conjugate transpose. So we have a 2 by 2 image. So you'll be having A00 conjugate, A01 conjugate, A11 conjugate, as well as A10 conjugate. Okay. You'll be having 4 elements: A00 conjugate, A01 conjugate, A10 conjugate, and A11 conjugate, since I have a 2 by 2 matrix. So A00 conjugate, in order to find out the A00 conjugate, as I said, to find out the kth element, I take the kth column and multiplied it with the lth column transpose. So you'll be getting the kth coefficient. So in order to get the 0th coefficient, I have to take the 0th column. 0th column is this one, 0th column of A, that is 1 1. So I have 1 1 multiplied with again A00. So the 0th column transpose. 0th column is 1 1. So 1 1 transpose. Here I have a 1 by root 2 outside. So 1 by root 2 into 1 by root 2. So I will be having 1 by 2. Similarly, in order to find the 0 1 star, you have to take the 0th column. 0th column is 1 1 into 1's first column transpose. First column is 1 minus 1. So you have 1 minus 1 transpose. So you will get the value for A01 star. Similarly, A10 star, 10 star, you have to find out A10 conjugate. That will be actually equal to A01 will conjugate will be equal to A10 conjugate transpose. Then A11 star will be, I have to take the first column. First column is first column and first column transpose. Okay. So first column is 1 minus 1. So I have 1 minus 1 into first column transpose. First column transpose is 1 minus 1. So 1 minus 1 into 1 minus 1 transpose. So multiplying this, you will get this. And you have 1 by root 2 common to both. So you will be having 1 by 2 into 1 minus 1 minus 1 1. That will be A11. And so similarly, you can find out all the values of the basis images. So these are all the basis images. We can verify the inverse. We know the expression A conjugate transpose V A conjugate will be equal to U. So substitute for A conjugate transpose. A is given. We already find out the value for V. A conjugate, substitute for A conjugate. Since it is real, there is no need to take the conjugate. Multiply this and verify. You will get the value same as equal to